It was a rainy Thursday night at 11:43 p.m. A call came into the city police control room. A wealthy businessman had been found dead in his farmhouse in the outskirts of the city. For over 20 years, Rajesh had built one of the most successful construction companies in Bengaluru. To the outside world, he was a self-made entrepreneur. But behind the scenes, things weren't so perfect. Just a few months before his death, Rajesh had gotten entangled in a 20 crore business dispute with one of his partners, Suresh. At the same time, he was fighting a bitter property case with his younger brother, Ramesh. And only a few weeks earlier, he had fired Sunil, a senior employee, accusing him of leaking confidential company documents. 3 people, 3 motives, 1 murder. The case landed on the desk of ACP Arjun Rao, a veteran crime branch officer with over 20 years of experience. Over the course of his career, Arjun had investigated more than 500 murder cases. He was not just an experienced detective, he was also a firm believer in data. Over the years, he had digitized several case files and used statistical models to uncover patterns that were impossible to spot with intuition alone. In fact, Arjun had a bigger goal. He wanted to train a machine learning model that would learn from his past experience and would assist him in predicting who the murderer is. Let's break down how a human would approach this. The problem here is to find out who the murderer is. As a human, I would first make an initial assumption and then I would look at clues and evidence to strengthen that initial assumption. Now, think about how a machine would try to solve this. An algorithm called naive Bayes uses similar steps. Once trained, the model uses Bayes' theorem under the hood. Bayes' theorem might look intimidating at first, but the idea behind it is simple. You start with an assumption called prior. Then you update this assumption when new evidence appears. This updation happens with the help of a probability called likelihood. In our story, the moment Arjun looked at the case, he had a hunch. Among all his suspects, the most likely to be guilty was the business partner Suresh. Not because he had found any evidence against him, but because he had seen hundreds of cases like this before. Now, coming back to the model Arjun was training, for the sake of simplicity, let's assume it's an intern in his office. Like an intern, it learns from a dataset that Arjun has created over many years, including 500 similar cases, out of which 250 involved business partners, 150 involved family members, and 100 involved former employees. Arjun's instinct pointed in one direction. The model also says that the numbers seem to agree. The assumption made is known as a prior probability that we defined in the theorem. This is one of the parameters that is learned during the training phase. However, intuition and past experience alone cannot solve a murder. Arjun needed evidence, and soon he found his first clue. Investigators discovered that Rajesh was recently reviewing his company finances over the past few years. It wasn't proof of anything, but it was interesting. So Arjun did what he always did. He compared the clues against hundreds of cases that he'd already solved. In many cases that involved business disputes, the victim often went through old transactions and company records shortly before things escalated. That made sense because if money was in the center of a conflict, digging through financial records is the exact kind of behavior you'd expect to see. Now, could this happen in a family dispute? Sure. Arjun had seen a few cases where it did, but not very often. Family conflicts usually revolve around relationships, inheritance, and property. Company transactions rarely sat at the center of these stories. And former employees, that was possible too, but those cases usually followed a different pattern. Now, let's see how our intern looks at the same clues. Unlike Arjun, the intern or the model doesn't have instincts, it only has data. So, it goes back to the 500 cases and starts counting. Out of 250 cases where the murderer was the business partner, in 180 of them, the victim was reviewing old company transactions. So, the likelihood of seeing this clue, given that the murderer was the business partner, is 180 by 250. That's 72%. Next, the intern or the model asks the same question for family members. Out of 150 cases where the family member was a murderer, in only 15 cases, the victim was reviewing company transactions. So that likelihood becomes 15 out of 150, that is 10%. And finally, for former employees, out of 100 former employees that were murderers, in only 10 of them was the same clue seen. So the likelihood there is 18 divided by 100, that's 18%. These probabilities are called likelihoods. And they answer a very specific question. If a particular suspect category were responsible for a murder, how likely is it for us to observe this clue? The clue that the victim was going through his company's financial records recently fits the business partner story more than anything else. Suddenly, Arjun's hunch wasn't just a hunch anymore. It is now backed by evidence. Arjun arrived at a conclusion. The most likely explanation was that Suresh, the business partner, was the murderer. Now let's rewind and see how the model learned how to do this. During training, the model learns two things. One is the prior probability, that is the initial assumption, and two is the likelihood. Likelihood tells us how likely we are going to see the clue given that we know the murderer is this particular person. That's it. When a new case arrives, the model looks at its prior probabilities and then the evidence. Using Bayes' theorem, it combines what it believed before and what new evidence came in. For every possible explanation or every possible class, it multiplies the prior with the likelihood. The resulting values are then normalized so that all probabilities add up correctly. These updated probabilities are called posterior probabilities, and the model finally chooses the explanation that has the highest probability. A detective follows clues to solve on this tree. Naive Bayes follows probabilities to make a prediction.